In this video, our goal is to understand the basics of a significance test. A significance test is one of the inference procedures that we can run in statistics in order to justify a claim. So there's two different types of statistical inference, right? The first one we've learned, which is a confidence interval. We use that when we want to estimate a population parameter, whether that's a proportion or a mean. A significance test we're going to use to assess the evidence provided by data about a claim concerning a parameter. So if I were to say that, going back to the example that the King's Page used for students with their favorite candy, the King's Page, our school newspaper, said that 30%, I think was the number, 30% of students say that their favorite candy is candy corn. Well, we could use a significance test to determine if that claim is true or to determine if they're wrong. So here's the actual definition of a significance test. A formal procedure for using observed data to decide between two competing claims called hypotheses. The claims are often about a parameter. So here's what a hypothesis is. A significance test will start with a statement of the claim that we want to compare. The claim we weigh evidence against in a statistical test is called the null hypothesis. The null hypothesis is denoted with this little 0 in the subscript. Often this is a statement of no difference. So if I wanted to say, if the newspaper said that the proportion of students whose favorite candy was candy corn, we're going to say the null hypothesis is that proportion is 30%. That would be my null hypothesis. Sorry, 30%. The alternative hypothesis is the claim that we're trying to find evidence for. So we hear 30% people saying that that candy corn is their favorite. I don't buy it. I would say that my alternative hypothesis is that the proportion is much lower than 30%, right? It's a change from what the claim was. So when we talk about an alternative hypothesis, it could be one-sided or it can be two-sided, and I'll show you some formulas for that in a second. The alternative hypothesis is one-sided if it's stated that the parameter is larger than the null hypothesis value, or if it's smaller than the null value. So for example, the candy corn example I was talking about, I think that it's much less than 30%. So that's going to be one-sided. I think it's less than 30%. A two-sided would be that if, in general, it's just different from the original claim, right? You could say, it could be less than 30%. It could be more than 30%. That would be two-sided. It's either less than 30% or greater than 30%. So here's a little easier version to look at. The null hypothesis has the form. The null hypothesis is the parameter which is equal to its value. So the King's Page claimed that the proportion, the true proportion of kids who think candy corn is their favorite is 30%. Say I wanted to run a one-sided, I would say my alternative is, hey, it's got to be different. That true proportion is actually less than 30%. Or you could say, actually, I think it's greater than 30%. Both of these alternative hypotheses are one-sided. They're both one-sided. It's either less than the original claim or greater than the original claim. The alternative being two-sided, if the alternative was, hey, I just think it's different from the claim, I think that it's just not equal to 30%. Really what this claim is saying both of these together. It's either less than or greater than. This would be an example of a two-sided alternative hypothesis. So remember, the null hypothesis is the claim. This is the original claim. The alternative is one of these three, something different from the claim, whether it's smaller than, greater than, both being one-sided. You would only have one of those. If you wanted to use both, you would use the two-sided claim. If you wanted to check both, you would use a two-sided claim. So let's look at this example really quick. At the Hawaiian Pineapple Company, managers are interested in the size of pineapples grown in the company's fields. Last year, the mean weight of a pineapple or pineapples harvested from one large field was 31 ounces. So the mean weight was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wondered how this change will affect the mean weight of pineapples grown in the field this year. So we need to state an appropriate hypothesis for performing a significance test. Be sure to define the parameters of interest. So the parameter that we're looking for, we are concerned about the weight. The parameter of interest is the mean or average, the mean weight of pineapples harvested. So we're talking about a new year with a new irrigation system, right? Assuming that the irrigation system does nothing different, I would say that my null hypothesis is that my mean weight stays the same, right? If my mean weight stays the same, that should be 31 ounces, right? I put in a new irrigation system. I'm assuming that if everything is the same, well, this next year, this next season, the mean weight of all of the harvested pineapples will still be 31 ounces. Now, the alternative would be if it changed. Now we need to think, do we care about change in general? Do we care about the pineapples decreasing in average weight or increasing in average weight? Here, we're just talking about a difference in general. So this will be two-sided. I'm going to say the mean is not equal to 31, right? This is just saying it's different. Not greater than, not less than, just different. So it's two-sided. And that's it. Those are our two hypotheses for this significance test if we were to choose to run it. So let's talk about actually running a significance test. But before we run the significance test, it's really important that you write down your hypotheses before you actually see your data, before you actually run your test. You wouldn't do a science experiment knowing the outcome and then write in your hypothesis, so you wouldn't run a significance test doing the same. So just to kind of help guide our thinking, here's an example. A virtual basketball player claims to be an 80% free throw shooter, right? Here's his claim. He's claiming to be 80% free throw accurate. Let's suppose we watch him shoot 50 free throw shots and he makes 32 of them. Based off of this one sample of 50 free throws, what is his proportion of making free throws, right? Well, we know P hat, right, this one sample of 50, he made 32 of them, right? Making 32 of them, P hat is 64%. So he's claiming that he has an accuracy of 80%, but based off of the 50 that we just looked at, he had an accuracy of 64%. So let's ask this guy to do many of these free throws over and over and over. We're going to look at 50. Remember, each of these samples of 50 is going to have a different proportion of accuracy because of sampling variability. And we're going to end up building a sampling distribution of sample proportions, right? And here is that distribution. Well, let's assume here that there are 400 samples of 50, right? Sample size was 50. This is a sampling distribution of sample proportions, right? Tells us right here, sample proportions. The 64 is right here. The 64 is right here. He is claiming, his claim was that he had an 80% free throw accuracy. So his claim, let me make this bigger. His claim is that that's where his true accuracy is. However, the one sample, even though it was just one, the one sample that we collected is over here. So we need to think, based off of the one sample that we collected, is his claim true? Is it wrong? And we can use that by running a significance test. So our observed statistic of 64% is so unlikely that if the actual parameter of 80%, that gives us convincing evidence that the claim is not true. Let me rephrase that. The 64%, there's such a small chance of it actually happening. There are two different scenarios that can happen. The first scenario is, well, maybe he actually does have a free throw of 80%. Maybe he actually has that true claim. And just by chance, what we saw was the warm-up, or what we saw was just so unlikely. Maybe there was a fluke, maybe there was an error, but it could still happen. It's not impossible. There's just a very small probability of it actually happening, what we got, but we saw it. That's one possible outcome. The other is that, well, maybe he's wrong. Maybe his free throw isn't 80%. Maybe it's actually 65%, right? If his free throw is 65%, then it wouldn't be surprising for us to collect a sample of 64%, right? So there's two different outcomes. The claim is true and what we saw was very unlikely, but it did happen. Or maybe he's wrong and the claim is different, right? Those are the two possible outcomes. So here's the basic idea. An outcome that would rarely happen if the claim was true is a good evidence that the null hypothesis is not true. Right? An outcome that would rarely happen if the claim was true is good enough evidence that the claim is not true. That's the basic idea of a significance test. So let's talk about what a p-value is. The null hypothesis, the original claim, right, states the claim that we're seeking evidence against. The probability that measures the strength of evidence against the original claim, the null hypothesis, and in favor of the alternative, what we're trying to find, is called the p-value. The p-value is a probability. Small p-values are evidence against the null hypothesis, against the claim, because they say that what we saw, what we observed, what we collected is unlikely to occur if the null were true. So how do we interpret a p-value? What is a p-value? The p-value is the probability of getting the sample that we got, or as extreme as what we got, if the claim were true. So in our example, right, we want the probability that we get the sample that we collected, right? We collected a 64% accuracy free throw sample. We think that maybe he's shooting less than the 80% accuracy. So this is going to be one-sided. All right, here's our one-sided. Let me write our claims really quick. The null hypothesis is that the true proportion is equal to 80%. That's the original claim. I think that's way too high, so my alternative hypothesis is that that true proportion is actually less than 80%. This symbol in my alternative hypothesis is going to determine what symbol I'm using in my p-value. So I want to say the probability that I collected a sample of what I actually got, or smaller, right? Maybe it was 60% accuracy. Maybe it was 20% accuracy, right? The probability of getting the sample I got or less, given that the true population parameter is 80%, right? Here's that conditional probability. The probability of what I got or more extreme, given that the claim was true. Let me write that in Word. The probability of what I collected or more extreme, given the claim is true. That's what a p-value is. That conditional probability, given that the claim is true. Right? So if I were to go back to my distribution up here, right? Let me erase this star. Everything that's circled is part of my p-value, right? The probability of getting what I got or more extreme, right? Anything less than, how many were there? There are 3. So my p-value here is 3 out of the 400 observations. That's a very, very small p-value, right? Let's see, less than 1%. Let me throw that in a calculator. 3 divided by 400, right? This is equal to 0.0075, right? There's a very small chance of what we got. So let's look at another example and see if we can interpret a p-value here. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommend a calcium intake of 1,300 milligrams per day for teenagers. The National Institute of Health is concerned that teenagers aren't getting enough calcium. Is this true? So researchers want to perform a test of, right, the original claim. We need to make sure that they're getting 1,300 milligrams, right? That's where we get our null hypothesis based off of our claim. We're concerned that they're not getting enough. So if we're concerned that they're not getting enough, we're only going to focus on what if they're actually getting less than what we need, less than what we need. That's how we can determine this is one-sided, right? If we were just concerned that it was dangerous to get more calcium, right? We don't care as long as it's only 1,300, then we would do two-sided. But here, since we're concerned with not getting enough, we're going to look at strictly less than. So where M is the true mean of daily calcium intake for the population of teenagers. They ask a random sample of 20 teens to record their health, food, and drink consumptions for one day. The researchers then compute a calcium intake for each student. Data analysis reveals that the sample average, X bar, is 1,198 milligrams with a sample standard deviation of 411 milligrams. After checking the conditions were met, researchers performed a significance test and obtained a p-value of 14%. So explain what it would mean for the null hypothesis to be true in this setting. If the null were true, then teens, let's say teenagers, are getting enough, or say getting the recommended dosage of calcium. If the null were true, if our null were true, that's saying that, yeah, teens are getting enough calcium. Interpret the p-value in context, right? So based off of the average that I get, I'm going to do it up here. The p-value, remember, is the probability of the sample being, look at our alternative, we're looking at less than. So the probability of our sample average being less than what we actually collect, so 1198, given that the true average is equal to 1300, right? So assuming that they are getting what they need, what's the probability of our sample happening, or even something more extreme, by collecting less than what we got? So to interpret that, right, we can say there is a, what is it, 14% chance of obtaining a sample average of 1198 milligrams or less, given that the claim is true. That's what the p-value means. So let's talk about statistical significance. What does it mean to be statistically significant? In the end, we will either reject the null hypothesis, which remember is the original claim. In the end, we're going to reject the claim, or we're going to fail to reject the claim. In stats, we're never going to accept. We will never accept a claim. We will never use language to imply that we believe a claim is true. We only reject or fail to reject. These two phrases, reject the null or fail to reject the null, will become very important in your vocabulary. So in the free throw shooter example, because the estimated p-value was less than 1%, because it was so small, there's strong evidence against the claim, right? What we collected, there's such a small probability of that actually happening. We're going to reject the claim, right? Because of that, we're going to reject the claim in favor of the alternative. Notice how I say we reject the null hypothesis. We reject the null hypothesis. I didn't say we accept that the proportion is lower. I don't accept the alternative. Remember, we only reject the null or we fail to reject the null. So here we're rejecting the null hypothesis. For the teen calcium study, right, the one that we just did, right, there was a 14% chance of getting the sample that we got. So would you reject the original claim, or would you fail to reject that original claim? What is the marker? What is the cutoff, right? So here we're going to fail to reject, and I'll tell you the cutoff number right now. That all has to do with the significance level. So for a significance level, the p-value, right? In order to reject, if we have a small p-value, we're going to reject the null hypothesis, right? If we have a large p-value, we're going to fail to reject the null hypothesis. There's no rule for how small of a p-value is required. It's a matter of judgment based off of your circumstances, based off of previous experiences and experiments, right? But what we have to do after we run the test is we have to give ourselves a marker. We have to say, okay, if I get a p-value less than 5%, right? If it's less than 5%, I'm going to reject the claim, right? Maybe it's really important. Maybe you're dealing with the health of people. Maybe you're dealing with a new drug that's supposed to cure cancer. So maybe you're going to look for a p-value less than 1%, right? You get to determine that at the very beginning. This is called its significance level, and we label it using the letter alpha. So this is something we've already talked about, but now let's put it in reference to the significance level, right? If our p-value is less than alpha, our significance level, we're going to reject, right? A small p-value, we're going to reject the null hypothesis. If our p-value is greater than or equal to our significance level, we're going to fail to reject it, right? We don't have enough evidence for our alternative. So what is this? On average, the random number that everyone agrees on, if it doesn't tell you a significance level or you don't need to think or justify a significance level, you will always use a significance level of 5%. This is always a good marker. Always use 5%. If you're dealing with the lives of people, you may want to go down to a 1%. If you're going to allow a little more error, you can go up to 10%, but usually you're good with sticking at 5% for a significance level. So remember, we're not accepting, we're only rejecting the null or failing to reject the null, but we could technically be wrong. Remember, there are different outcomes. We could be wrong in our judgment, in our significance test, and so we're going to make an error. And there are two specific types of errors. If we reject the claim when it's true, right? We reject the claim even though it's true, we have committed a type 1 error. We call that a type 1 error. We reject the claim even though it's true. If we fail to reject the claim, right, it was like, it could actually be true, it could, so I'm not going to reject it, it could be true, right? When the alternative is true, then we've committed a type 2 error. It takes some time to kind of get used to this. Whenever we reject and it is true, we've committed a type 1. Whenever we fail to reject the null hypothesis, when the alternative is true, then we've committed a type 2 error. So because of these errors, we get different outcomes. So here's an example. A potato chip producer and its main suppliers agree that each shipment of potatoes must meet certain quality standards. If the producer determines that there are more than 8% of the potatoes in the shipment that they have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. To make the decision, a supervisor will inspect a random sample of potatoes from the shipment. The producer will then perform a significance test using the hypotheses. The null hypothesis is that 8%. The alternative is that the proportion is greater than 8%. So, describe a type 1 and a type 2 error in this setting and explain the consequence of each. Well, remember, we have the null hypothesis. The null hypothesis, we said, is the proportion is at 8%. So a type 1 error is we reject this claim. We reject that it's 8%. When it's true. Type 1 error is when we're going to reject that claim, given that it's true. So what does that mean? When we have a type 1 error, we're going to say, the company sends back the truck or the potatoes. Meaning they have to wait to make chips. Results in a loss of profit because they might have to wait an entire day. The supplier also has a loss in profit. You need to think of all of the situations that can occur from this type of error, right? We look at the truck, we say we're going to reject that the blemished potatoes make up 8% of this truckload, right? If we reject that, we're assuming there's going to be more than 8%. So we send it away. We don't want to make chips with gross potatoes. And that's going to make our production be behind a day. We're going to lose money. The supplier has to take the potatoes back and potentially dump them. They're going to lose money, so on and so forth. Remember, my alternative was that the proportion is greater than 8%. I care about greater than 8% because I don't want bad potatoes for my company. So a type 2 error is when we fail to reject when HA is true, right? We fail to reject when HA is true. So I'm gonna fail to reject this claim. I'm gonna fail to reject that the proportion of this truckload is 8%, even though it's actually more than 8%. So what does that mean for my company? That means I accept the truckload and make chips with blemished potatoes. This will result in poor customer ratings. So far, let's talk about everything that we know about a significance test. When we run a significance test, we need to state the parameter of interest. We need to state our hypotheses. This is the null hypothesis and the alternative hypothesis. Technically, you can determine if the alternative hypothesis is one-sided or two-sided. After we state our hypothesis, we need to determine a significance level. Remember, that's alpha. If you have no idea, when in doubt, choose 5%. Alpha needs to be 5%. After that, you need to collect a sample. This is p hat or x bar. Calculate a p-value. And then conclude results. So you can say that these are all the steps of a significance test.